Good morning, everybody. Welcome to the one of the perhaps historic days in our institute, and this is connected to the fact that we are delivering for the first time the ETH Zurich Chemical Engineering Award, and this medal is conceived to honor an individual for outstanding contributions in any of the broad areas encompassed by chemical engineering. And on this special occasion, the first recipient of this medal is Professor Ferdi Schütt from the Max Planck Institute in Mulheim. And this award is granted to Professor Schütt for the originality, depth, and relevance of his contributions in catalysis, in energy-related research, and in materials, in particular porous materials. So I would like just to briefly introduce the speaker, although most of you will agree with me that he doesn't need too much of an introduction. Professor Schütt studied chemistry in 1990, finishing with his doctorate in 1988 at the University of Münster. And 1 year later, he also finished his studies in state examination in law. So it's a very interesting thing. And although he is a chemist from a training at the university, he started his research activities at a much earlier state. He started his own lab, as many of us at home. And soon, when he was a kid, and soon after a few experiments, the lab was banned to the cellar because he produced hydrogen sulfide in the kitchen. And this already reflected some, original character. Producing hydrogen sulfide in a kitchen is always very interesting. His career has been stellar, amazing. So he did postdoc research with a true chemical engineer, Lenny Schmidt, University of Minnesota. And then he went back as a research assistant with Klaus Unger. And he developed there at University of Mainz his interest for catalysis, visiting later on a well-known lab in Santa Barbara, Gallenstachy, where he did, he was a visiting assistant professor over there. And then he completed his habilitation and became a professor in University of Frankfurt, 1995. He was there 3 years, and after 3 years, he received the offer to become a scientific member of the Max Planck Institute for Coal Research. He has been director of that institute. And in addition, he is honorary professor at the University of Bochum, where he develops one of his other passions, which is teaching big classes of students what chemistry is supposed to be. His statistics in terms of publications and research interests, I think, are clear. Catalysis, high-throughput experimentation, biomass research, materials research, amazing visibility. His work has attracted over 23,000 citations. Every of his articles is cited almost 70 times, so I think this is impressive. And not only his papers are well cited, he also has many patents in the open domain. Prizes, obviously, this is a long list of prizes, and I would like just to mention a couple of them. The Leibniz Award of the DFG in 2003, the Wohler Award and the Hamburger Wissenschaft Award 2011, Wilhelm Klemm Award by the German Chemical Society 2012. And he is often ranked as one of the top material scientists in the world. Service, he also did a lot of service, and relevant for many of us are his functions as editor in editorial boards of many journals. In particular, He is editor of Chemistry of Materials, a very, very prestigious journal for materials research. And in addition, it's important to mention that he has been vice president of the German Research Foundation since 2007. I also would like to highlight other thing, which is not so frequent or becoming more frequent, but that's the entrepreneurial task. And that's the fact that, and I would like to mention this since I have been interacting with this company for several years. Professor Schutt is founder, member of the board of directors, and chairman of the scientific advisory board of HTE. HTE stands for High Throughput Experimentation. Is a company that was, in a way, originating in BASF, but it became independent, and several years after BASF realized that they want to have this company in the BASF group. And I think this was a victory for many of those that initiated this activity and basically were recognized by BASF that they did a very good job in developing tools and methodologies to do high throughput development of catalysts and materials. Well, this company employs 220 people nowadays, so you can see that this is very interesting and very successful. He wants people in his lab happy. This is, I think, very important. When you see his scientists around the world, they all smile a lot. I think the atmosphere in his lab should be fantastic. And the table football that he has, according to him, is one of the catalysts for part of this happiness. I would say that with this introduction, which I could make as short as I actually could, I would like to thank Ferdy Schutt for accepting this medal on behalf of the whole Institute of Chemical and Bioengineering, and I would like to hand him to Professor Schutt. Ferdy?
Many thanks. Wonderful.
The floor is yours.
Well, I don't really know what to say. First of all, thank you very much, Javier, for this very flattering introduction. I have to say, I quote very famous colleague, John Thomas, after this introduction, I'm really looking forward to hear myself talk. But also for the honor of awarding the very first medal of the Institute of Chemical Engineering to me. This really means a lot to me. It's a great honor, especially since I'm not an engineer, but a chemist. But I have had my strays into engineering, as you said. Working with Lenny was certainly somewhat engineering. So, as I said, I'm deeply honored to stand here in a department where there's so many famous chemists, chemical engineers have been working, and be the recipient of your first medal. Thank you very much. While I am not an engineer, I think one could argue that what we are doing, or what I will be talking about today, is to some extent actually engineering, but on the nanometer size scale. There is an element of engineering to it. When we look at the length scales in catalysis, well, this is the typical domain of the engineers. Big processes, developing reactors, developing unit operations, researching unit operations. But in catalysis, the scale from the reactor down to the level of basically the active site are all relevant. And you need to master all the different levels for optimizing a process, optimizing a chemical reaction, optimizing a catalyst. It's all part of the science of catalysis. And I want to talk about nanostructured catalysis, which is basically, well, sort of engineering on this size scale. Let's say between the nanometer, even sub-nanometer, to several 100 nanometers. But towards the end, I will also pose a real hardcore engineering challenge or address a topic where there is really hardcore engineering challenges on the big scale, a process which costs me many valves in the lab, probably new valves every 3 weeks, handling oleum for activating methane. That will be the final part, and that's again more towards the engineering. What I would like to cover with respect to the nanostructure control are a number of different topics. First, I would like to address placing particles at desired locations in pore systems to optimize the functionality. Then I will cover sacrificial templates, which also means placing particles where we really want them to fulfill a function. I will talk a bit about another function to make catalyst particles magnetic, to have possibility for an alternative separation may. And this here is the methane oxidation stuff where we tailor indeed the ligand environment around the platinum center to fulfill a catalytic function to activate methane, but it translates to a tremendous engineering challenge to really make a process out of it. And I think you will see that later on during the presentation. Now let's first discuss the placement of particles at desired locations in pore systems. And I already at this point want to introduce a rather complicated stepwise procedure for producing a catalyst material, which maybe gives you the flavor of what I mean by engineering on the nanometer scale. All these steps are actually quite difficult and tricky, and I couldn't do them. I have a number of really great, talented, dedicated students who really develop the processes to be able to achieve composites like this. This has been done by Joachim Nitz, actually, and the target was to produce a catalyst for ammonia decomposition. There are discussions that ammonia could be, at least in niche applications, could be a very good storage compound for hydrogen. Because if you decompose ammonia, the product is nitrogen and hydrogen, so it's a very clean hydrogen without any catalyst poisons you generate. So if you have a good way of decomposing ammonia, this could be used to release hydrogen when you want it in a clean form. And iron oxide is known to be, well, a good catalyst for ammonia synthesis, or the iron catalyst is the basis for the ammonia synthesis catalyst. So iron compounds should also microscopic reversibility, good catalyst for ammonia decomposition. Now, the way we try to produce these very small iron particles is actually we start with SBA 15, a hexagonally ordered porous silica where the pores are formed by basically templating from a surfactant liquid crystal in a very superficial description. So what you see here is tubes of silica and holes in the center of them. The holes here, size scale, maybe 6 nanometers approximately, wall thickness, maybe 2 nanometers, and you structure this by surfactant liquid crystals. Then you impregnate the inside of these tubes with carbon. You put a precursor for carbon in there. You can use many precursors. Furfuryl alcohol is what we normally use that polymerizes easily. And when we then carbonize without oxygen, you form basically a thin carbon layer on the inside of the silica tubes. Then we impregnate with iron nitride. So we fill the inside of the carbon tubes with iron nitrate. Then we heat treat and we convert the iron nitrate solution to iron oxide particles. And then we leach out the silica to have a pure carbon compound formed from tubes, hexagonally ordered, and only in the inside of the tubes, precisely located in these 4 nanometer holes, we have iron oxide particles, which can then not grow any further. That's basically a size limit which we have imposed on it. I hope you can see that reasonably well. This is the material, what it looks like. It looks like a woolen sock, actually, a knitted woolen sock. We are looking here at these hexagonally ordered carbon tubes. The tubes run in this direction. These are the carbon tubes, and you can actually see the carbon tubes in high-resolution scanning transmission electron microscopy. I'm always amazed what scanning electron microscopy can do nowadays. So you get nanometer resolution in a scanning electron microscope. This is actually not a badly done image with lots of charging. I have actually brightened it up to make the pores better visible in this micrograph. And what you see here is actually the carbon tubes extending out from this hexagonal array here. The carbon thickness, the wall thickness is approximately a nanometer, and the inner diameter of the tubes is approximately 4 nanometer. And since we have placed the iron oxide particles all within the tubes, well, you basically don't see anything on the outside. Occasionally you find an iron oxide particle on the outside of this carbon arrangement, but in principle, it's all inside the tubes nicely embedded. You can see that, and now this is transmission electron microscopy, when you cut it perpendicular, so if you cut it through here, if you cut it through here and then look perpendicular on the sample, then you see basically all these iron oxide particles. Here are 3 adjacent channels and then filled with an iron oxide particle in the channel. So here you see an empty channel. It's difficult to see in this image, but it's basically, they're all the same size, all the 4 nanometers fixed in the channel where we have placed them at will. And these catalysts are actually, at the time when we synthesized them, were the most active iron oxide-based catalysts for ammonia decomposition which were known. Ruthenium is better with respect to activity, but ruthenium is way more expensive. So large processes you wouldn't base on ruthenium. And the catalyst is stable over, well, at least 20 hours a year. This is the time we ran it. This shows you a nice example, I would say, for this nanoscale engineering, if we may call it like this. Later on, we found actually a simpler way to produce a stable iron-based catalyst, which is also nice, especially because we prepared a nice benchmark system. It uses a similar concept, encapsulation of iron particles in a porous shell, but it works in a different manner. Here we start with iron oxide particles. We start here with alpha iron oxide, but you can also use the gamma depending how you make the nanoparticles. Sizes approximately 30, 40, 50 nanometers. And then we coat the iron oxide nanoparticles with a porous silica shell, and we create porosity by adding a surfactant again, which we burn out afterwards, and that creates then the pores in the silica shell. And if we run then catalytic ammonia decomposition, it's again for generation of clean hydrogen, actually the iron oxide is converted to iron nitride species, different types of iron nitrides. And this is a pretty nice and active catalyst, actually more active than the one I have shown you before, and it's stable. And the reason why it's stable is that we have encapsulated this iron particle in the porous silica shell so that 2 iron particles will never meet each other and can never sinter together. And this is why I like this work, because Matthias Feyen, who did it, actually made a wonderful benchmark catalyst which allows you a direct comparison of the encapsulated and a reference catalyst. The encapsulated catalyst is stable over time here. This is something like 30 hours. The reference catalyst loses activity. And now I show you what the different catalysts are. This is the iron oxide encapsulated catalyst. So iron oxide in a silica, porous silica shell, under reaction condition converts to iron nitride. But Matthias Feyen synthesized the reference catalyst by taking such a sample here, coating it with porous silica, coating only half of this, the other half he set aside of the iron oxide nanoparticles, coated it with silica, and then leached the iron oxide out with hydrochloric acid. And that gave him empty silica shells, and then he added the other half of the iron oxide nanoparticles to this sample. So he had basically an identical sample, one where he had the iron oxide encapsulated, one where he had the iron oxide particles, and separate empty capsules. And if you look what happens after reaction, well, those of you working with catalysts can imagine what would happen. This catalyst hasn't changed. The iron oxide is still encapsulated by the porous silica, but here we have big blobs of iron nitride, or oxided. If you take it out of the reactor, you have this oxide surface coverage, oxided iron nitride catalyst. So this is the reason why you lose activity here while these protected ones retain their activity. We will see similar examples also further in the talk. There is another possibility of encapsulating catalytic particles in pore system, and this is something we did with the group in Lyngby, in a cooperation with the group in Lyngby, Søren Kagnas, for instance. The goal was to put nanoparticles, metal nanoparticles, gold nanoparticles in this case, into a zeolite, so that the gold nanoparticles can only be accessed through the pores of the zeolite, through the sharp, narrow pores of the MFI zeolite. So we have in the zeolite gold nanoparticles, but the access to the gold nanoparticles is only provided through the 5.5 angstrom big pores of ZSM5. This is the matrix. And the way we do it is basically prepare colloidal particles, pre-prepare colloidal particles, and Alfons Beiker is one of the pioneers to use these preformed colloidal particles and occlude it into silica and then expose it to the synthesis conditions for a zeolite. And then you convert the silica to the zeolite, whoops, too far, the silica to the zeolite, and then the particles are only accessible through the zeolite pores. And that creates selectivity for catalysis. The reference catalyst here is gold on titania, and we have looked at air oxidation of aromatic aldehydes, methyl benzoate, and then this very bulky methyl benzoate. If we don't have the gold in the pores of the zeolite, if they are just on titania, well, basically methyl benzoate and the bulky reference compound are converted at approximately the same level. If we have the gold in the inside of the zeolite, where only the small molecule can reach the gold particles, but the big bulky reagents cannot enter the zeolite pores, the small methyl benzoate is converted like on the gold on titania catalyst. But this bulky substrate cannot enter the zeolites, can never reach the gold particles, and thus we do not observe any conversion here. So if you place particles protected by a pore system, you basically have sort of a molecular sieving effect like it is known for zeolites, and we achieve this in this case by incorporating the particles. Very recently, Ryan Wang, who is also here today, has developed another method for encapsulating noble metal particles into a pore system. And I like this work conceptually very much, because what it essentially is we create a palladium polyphenylene catalyst by a Suzuki coupling, and then we use the product of this Suzuki coupling for catalyzing a Suzuki coupling. Maybe it's not good for anything, but I just like the concept of doing something like this. The way Ryan did it was he used a Suzuki coupling of these two substrates, the boronic acid and a aromatic bromine compound, catalyzed by palladium to create this polyphenylene. This is a porous, sort of intermediate between graphene and carbon nanotubes, so to say. It's a porous carbon material with very high surface area. And in the process of producing this catalyst, the catalyst for the Suzuki coupling to create the catalyst is actually converted to metal particles which are embedded in the pore system of the polyphenylene. It is very porous. Well, it's a microporous material, so BET surface area has to be taken with care, interpreted with care, but it's a very porous material, roughly 300 cubic centimeters per gram. Pore volume, if you calculate something like a BET surface area, it's about 1,000 square meters per gram, so it's a highly porous material. And if you use that for a standard Suzuki coupling, it's actually a pretty good catalyst. In 24 hours, almost 100% yield. We have a side reaction, the coupling of the boronic acid with itself. But if you look at it, we can activate chlorosubstrates with this catalyst. It's just aqueous phase. We don't need a phase transfer catalyst. It happens all in the polyphenylene, in the porous polyphenylene, and you can recycle several times without much loss of reactivity. So I think this is quite an interesting concept, to place noble metal particles in a pore system by a reaction for which you then later catalyze by the catalyst created. Now let's move to the next topic. Sacrificial templates is something we very often use to achieve the quotation marks engineering goals we have in creating composites with well-defined properties. And I'll address two different topics: CO oxidation over gold catalyst, and then the extension of the concepts to fuel cell catalyst. The work started actually quite a while ago, more than 5 years ago, with work by Pablo Arnal and Massimiliano Comatti. And they came up with the idea to make a sinter-stable catalyst by encapsulating the active catalytic particle in a shell, in a cage, with pores which are smaller than the particle itself. So then the particles can never leave their cage and can never meet each other and can never sinter, at least if the sintering is particle-to-particle coalescence and not atom migration, which can also lead to sintering. But particle-particle coalescence by this pathway is completely suppressed because the inner particles here can never get out of the cage if the pores are sufficiently small. The way to do it is you start with a gold cluster, in this case 15 nanometer in size. They work best, one has to say. We would like smaller gold particles, but the 15 ones are the best, actually. Then you take the well-known Stöber process to make monodisperse silica particles of approximately, well, we can adjust the size between, let's say, 50 and 200, 250 nanometers. Then we coat the silica by a porous zirconia shell, and we use zirconia because it has very high thermal stability. And then we leach the silica with sodium hydroxide, and we have a gold particle in a porous zirconia shell. This is a nice cartoon. You can draw many nice cartoons in this field, but you should prove that you have what you claim you have. You can see that quite nicely with electron microscopy. Here is the gold particle in the center of the silica sphere. Looks a little bit like frosh eggs with the gold in the center. You coat with the zirconia, then it gets a little bit gritty here on the surface. This is the porous zirconia shell, let's say 10 nanometer, 20 nanometer thick. You notice gold is still in the center here because the silica keeps it there. And then you leach the silica, and you get this. And of course, then the gold particles are not in the center anymore because nothing keeps them there. They just fall somewhere onto the inside of the sphere, and this is where they end up. But they cannot leave the hollow shell because the pores are too small for the gold to get out. If we test these catalysts in simple CO oxidation, just as a test, they convert CO actually for the particle size we have relatively nicely, 50% conversion for the conditions we use at 180 centigrades approximately. These are not the most active gold catalyst. You need much smaller particles to get higher activity, but that's not bad for the 50 nanometer size. If we calcine this sample at 800 centigrades, it's essentially the same conversion curve. So no loss in activity. If we crush the spheres so that the shell is broken, and we do the same experiment, calcine at 800 centigrades, activity is lost, and the reason is that the gold particles now sinter and form big gold particles. We don't have the protection anymore. This is the image, and I would like to thank Heiner Friedrich and Krijn de Jong for doing this tomography analysis, where we can really see that the gold particles are individually encapsulated in the zirconia shells. What they do is basically they they record 170 electron micrographs and tilt the sample stage by 1 degree after each micrograph. And then in a computer, they reconstruct it to a 3-dimensional representation of the sample. And this is what you now see. And then you can also play tricks on the computer. You can actually highlight the gold particles and the shells, and you take them out for the analysis. So here you see, this is artificially the gold particles taken out by image processing. But you can see these shells are shells and they are intact. The next one you see, they only took the gold particles and removed the shells, and you see all the gold particles basically have the same size, and they're all isolated. They are not two hanging together. And now they put everything back together, and you can, let's say, focus on this particle. You see this is alone in this particular shell. This one here is alone in this particular shell, and this can be expected from the synthetic protocol. This is what you need to get. Perfection is actually pretty high if you have an optimized system. I would say approximately 95% of the shells contain exactly 1 gold particle. Some of the shells contain 2, some of the shells are empty, but it's a pretty reliable and precise procedure. And now we went about to play with it. We can shrink the sizes and or expand the sizes, but we also wanted to decrease the size of the gold core, not just of the zirconia shell, but also of the gold core. And the first idea you come up with is, well, why don't we partly leach out the gold by just dispersing it in aqua regia, which leaches the gold? Well, you can do that. Here you see dispersed in aqua regia, size reduced by a factor of 2. You can actually take all the gold out, then you have silica particles with a tiny little 15 nanometer hole in the center, which you can then refill with something else. I don't want to discuss that today. So you can, by controlled leaching, actually reduce the size. But if you do that, well, this is the conversion curve for the native material. But if you leach, you lose all the activity. Surprising at first, but if you read a little bit about gold catalysis, CO oxidation, you find chlorine is a poison for these catalysts. So you don't want chlorine. And then you look into your, or go back to Inorganic Chemistry 101, and you find gold can also be leached by cyanide, which Haruta has actually done. So we do cyanide leaching, leach it to 10 nanometer, and you can do it stoichiometrically. You can just add the right amount of cyanide. You know what size you will get afterwards. And then you basically retain the activity, although you have leached half of the gold off the sample. Then we did series of leachings. The size distribution for the smaller particles gets wider here. But what we basically see is all the catalysts are active. We have different activities here, but you have to normalize to surface area to get real information on the intrinsic activity. And what the bottom line of this analysis is, for these particles sized above 5 nanometers, turnover frequency, catalytic intrinsic activity is essentially independent of the particle size of the gold. So the high activity really only sets in at smaller particle sizes below 5 nanometers. Now, obviously, we would like to produce particles which are smaller than 5 nanometers by this leaching protocol. But we run into a problem then. If you reduce from 5 to 15, from 15 nanometer to 5 nanometer, you have removed more than 90% of your gold. Actually, it's a factor of 27, goes with the power of 3. So it basically means from your initially present 2–3% of the gold, you are down to 0.1%. And then small irregularities in the leaching process leach some particles completely, and some are left in a little bit bigger size. And then you lose the control over the process. And we haven't managed to get smaller particles by the leaching protocol here, and so we are left with this. You can also do other things, also fundamental studies of these gold catalysts. You can dope with titania, which is supposed to be an activator for CO oxidation catalysts, gold-based CO oxidation catalysts. So we coat, for instance, here in this case with a little bit titania, then we coat with silica, then we coat with zirconia, then we leach the silica, and then we have a gold particle decorated with titania here in a zirconia shell. And this is a somewhat busy slide with lots of data points, but basically what is plotted here, let's take the solid points here. It's the temperature for 50% conversion over the titania content decorated onto the gold particles. And there is a very clear trend. If you increase the titania doping, your activity goes higher because 50% conversion temperature decreases. So titania really in this model catalyst really has a beneficial influence on catalytic activity. Now the next step was, and this is already on the way to fuel cell catalysts, the next step was, let's try to change the shell material. In a fuel cell, you want carbon as the support because you need a conductive support for a fuel cell catalyst. Now carbon you cannot directly coat onto the silica. We tried that, but you don't get a nice coating of a porous carbon shell. But what you can do to create a carbon shell is actually you stop at this point here, you don't leach at this point, but you take this first product as a binary template, infiltrate the pores here in the zirconia with some sort of polymer. This can be furfuryl alcohol, but this can be many other polymers which carbonize well. Then you carbonize, heat at high temperatures, 800 centigrades in protective atmosphere or vacuum. So then you create carbon, the carbon zirconia composite coated on a silica, coated on a gold particle. And then you can leach either separately, first the silica, then the zirconia, or both at the same time. And at the end, you get a gold in a carbon shell. It actually turned out later, the better way to do it is not produce zirconia on a silica shell, but produce porous silica on a solid silica shell and then fill the pores in the porous silica. But that's a detail about which you don't need to worry. It's just the quality of the materials gets better. So just that you see we can do it. This is now the silica-based, so gold in solid silica, in porous silica. So here is the gold in solid silica. Here it's coated with porous silica. Then we fill with the polymer here and carbonize, and it looks pretty much the same. And then we leach out the silica, and now we have the gold the gold particles in a porous carbon shell. So we have replaced the zirconia or the silica by carbon, by this repeated templating process. This gives you basically the same information, but it looks a little bit nicer. So I like these color images. What they actually are, this S5500 microscope, it's a Hitachi high resolution or ultra high resolution scanning electron microscope, where you can actually switch between scanning and transmission image. It's very same image. You just switch the detectors. One point you have the transmission, one point you have the scanning image. So this is the scanning image where you see the surface of the particle. This is the transmission image where you basically see through the carbon shell and see the gold particle. And this here is the overlay, which gives you this sort of three-dimensional representation where the transmission image is colored in green and the scanning image is colored in red. And then you can actually hear the colors are inverted. Sorry about that. Actually never noticed this. So here you see the gold particles in the carbon shells. And now comes the interesting question, are the catalysts still active when they are in carbon? Because in gold catalysis, CO oxidation, there is always the notion you need an oxidic support. You need oxygen from the support to assist in the gold catalysis. And ho behold, as long as there is oxygen in the shell, either here gold zirconia or gold in the carbon zirconia composite, activity is high. As soon as you leached, and in the brackets I just indicate what is leached out, it's not present anymore. This is really gold in carbon made from the porous silica, gold in carbon made from the porous zirconia. These are smaller gold particles. Activity is strongly reduced. So a good oxide is actually very beneficial for high activity in CO oxidation. Now let's move then to fuel cell catalysis. In a fuel cell, you basically decouple the reaction between hydrogen and oxygen German, the Knallgasreaktion. I'm not even sure whether there is an English term for Knallgasreaktion. I like this word, Knallgas, because it's very descriptive. And we decouple the reaction. We need platinum typically on carbon catalyst, and this is the catalyst we want to look at. On the hydrogen side, the hydrogen oxidation catalyst, the anode catalyst. And one of the crucial problems in these catalysts for commercial applications is actually corrosion of the carbon support and loss of activity. These catalysts are not long-term stable. This is one of the big problems which is often neglected. And we wanted to produce fuel cell catalyst. And the idea was, well, why don't we just take the very same concept, but put platinum inside, have platinum in carbon, and then it cannot be leached out, or it's more difficult to leach it out because it's stabilized in the shell. Well, it turned out you don't get enough platinum into these shells. Fuel cell catalysts have a typical loading of 50% noble metal on carbon. And it's almost impossible to get 50% platinum by this process into the shells. So these catalysts have mass activities overall normalized to catalyst mass, which is way too low. And so we had to stop this line of work. Fortunately, Carolina Galliano had a different idea how one could maybe stabilize the carbon particles. She said, well, why don't we just use this process and produce only the hollow carbon sphere, and then do not put the gold inside, but use these mesopores in the hollow carbon sphere to protect platinum particles and encapsulate them in the mesopores. So what she did was impregnate platinum into the mesopores, reduce with sodium boron hydrate, and then do a high temperature thermal treatment to encapsulate it and stabilize it in the pores. And this is what you get. This is a platinum on this holographitic carbon shell after treatment at 900 centigrades for 10 hours. So this is really a harsh treatment for a platinum catalyst. And you see platinum particles are, well, between 3 and 5 nanometers in size. They don't grow bigger than that. And this is ideal for fuel cell catalysts. And they are actually stable under the conditions of the fuel cell. And this is something we do with Josef Meyer and Karl Meyerhofer in the Max Planck Institute in Düsseldorf. They have developed the so-called identical location electron microscopy. They did that for TEM, and we extended that to SEM-TEM. What you basically do, you put your catalyst on a finder grid for the electron microscope, which has coordinates on them. You analyze the catalyst. This is what is done here. So this is a place on the catalyst, analyzed with both scanning and transmission. Then you put it on an electrode, put it in a rotating disk setup to do the electrocatalytic experiment. You take the grid out again. Since it has a coordinate system, you can find the same location again. And you see here are the two spheres again after the catalysis, exactly the same location, and then analyzed. And what you see is actually quite interesting. The number of particles, the size of the particles has not much decreased or changed. I'll show you quantitatively later. But actually the structure of the support has to some extent be changed. I mean, you can still sort of see some of the pores here and here. These are the same ones, but the structure actually, the graphite, the graphitic carbon actually corrodes quite substantially under the conditions of the electrochemical test, but it's still, since the platinum particles are confined in the pores, we don't lose them, they don't fall off, what normally actually happens. A major deactivation pathway is the noble metal particles just fall off the carbon support and then are just swimming around in the electrolyte. And this doesn't happen here, so we basically have the same performance afterwards. Here is again this nice overlay, it doesn't give you more information, just looks a bit nicer. And what we then see is, compared to commercial catalysts, this is the aging profile over many degradation cycles, 12,000 accelerated degradation cycles in this rotating disk setup. It deactivates actually quite rapidly, while this platinum on holographitic spheres has about twice the activity after the degradation test of 12,000 cycles. And if we analyze actually from the electrochemistry, we lose 18% of the platinum surface area during these tests. And if we analyze by identical location time how many particles we have lost, we lose 14% of the particles. So this agrees almost too nicely. This is really a very high stabilization. And these catalysts here, these commercial catalysts, lose about 50% of surface area and particles. So this encapsulation pathway indeed works very well. We actually have, I don't show the results, we have translated this to a real fuel cell catalyst. So the people in Duisburg at ZBT have really built fuel cells from these catalysts, and we see the same behavior in a real-world fuel cell. Now, platinum is not sufficiently active for commercialization of fuel cells, and the concepts to have a higher intrinsic activity actually to a large extent rely on alloying platinum with something else. And one alloying method is, for instance, nickel. Platinum-nickel alloys are supposed to be better. But here we run into a problem. For alloying, we typically need high temperatures. So here, for instance, we have platinum and platinum-cobalt alloy in this case. If you heat that to high temperatures, you get a nice homogeneous alloy. But if you heat it to high temperatures, you also get growth of particles. And that leads to reduction of the activity. You don't want big particles. The other possibility is first synthesize in solution the alloy particles, then deposit them on a support. But this is also not very good because you cannot nicely anchor these preformed particles on a support. And then again, Carolina and Stefano Mezzavilla had the idea, well, why don't we use these holographitic spheres, the pores in the holographitic spheres, as confining geometries to produce alloys on the nanometer scale? So if we fill one of these pores with nickel and platinum, we can heat it to form the alloy, but at the same time prevent growth because they're confined in these 4 nanometer pores. That was the idea behind it. This is the protocol we don't need to discuss in detail, and it actually works. If we treat at high temperatures, you see here the sizes. These are the alloy particles, size 2, 3, 4 nanometers. And the most important benchmark is then the electrocatalytic test. This is pure platinum mass activity. This is the platinum-nickel alloy. So we get a roughly 3-fold increase of the catalytic activity of this catalyst. And with this system, we actually meet the benchmark specifications of the US DOE for commercializable fuel cells. So we are really excited about this work and the stability. Yes, stability of these catalysts is approximately the same as for the confined platinum particles in the holographitic shells. If we cycle to very harsh conditions up to 1.4 volts, if we only do the cycling to 1 volt, which is the normal operation range, activity is basically stable over 12,000 cycles. But in a real-world fuel cell, you have start-stop situations with ill-defined conditions, then you can have potential excursions, and so this is something to worry about to some extent. Now, before we come to the final stretch of the lecture, a little movie just for relaxing. I want to talk about magnetic particles, and I had a very talented, gifted technician who often went to the lab for 2 months and then came later back and said, look what nice things I have produced. And they were normally really nice things. A very creative person. He worked like a scientist, but by training was a technician. And he, at one point, decided, well, why don't I make magnetically separable carbon catalysts? And there is something called Kugelkohle. If you haven't worked with this, Kugelkohle is a wonderful material. What it basically is, it's carbonized ion exchange resins. They are all the same particle size. They are roughly 500 micrometers in diameter, very hard materials. They basically flow. They're very nice properties as a material. And they are highly porous and very pure. So it's a wonderful material as a catalyst support, actually, and for also other reasons. And what Manfred did is he impregnated the Kugelkohle with iron nitrate and then just passed benzene or toluene vapor at high temperatures over it. And that led to the reduction of the iron nitrate oxide then to iron, and at the same time they were coated, the forming iron oxide particles were actually coated by a carbon shell which protected them against oxidation. So they retained magnetic properties, superparamagnetic properties. This is what you get, approximately 5 to 10 nanometer sized iron particles dispersed in this carbon shell. And this is now the relaxation part of the lecture. He then did a commercial video for this material where he placed them in a cuvette here with a switchable magnet. You can see you can just stir the solution with the magnet. He changes then frequency. It just looks nice. I mean, it all tells you it's magnetic. It's not more than that, but just for relaxation, it's not bad. Then he stirs it. There is no stir bar in there. It's just the magnet underneath. It's a strong magnet, but the magnetism of the iron impregnated carbon particles is actually not bad. Here he just, here you see how fast you can separate the carbon from solution. So it just sticks to the magnet and the solution is clear again. And the next one I think he uses, okay, so he transfers it. He's an organometallic chemist, so he does all these Schlenk techniques by transferring particles. Yeah, here he is transferred and it's stuck in the magnet here. So you can really make nice magnetic particles. We have done magnetic particles, and that comes back to this engineering aspect again, also based on other concepts. This is something Anhui Lu has done almost 10 years ago, again starting from these ordered mesoporous materials, where he placed a carbon precursor inside, so that he could only externally functionalize this material, because we wanted the pore system for something else. We wanted actually to place the catalyst there, and the magnetism should sit on the outside. So he protected the pores here, placed cobalt particles 9 nanometer inside on the outside, couldn't go inside because that was protected, coated with carbon, because cobalt otherwise would corrode, leached the silica, and then we had the pore system, the carbon pore system here, in which we could fill catalytically active materials. And you see, it's nicely magnetic. We can use it to decolor dye solutions. And here you can see these are all 9 nanometer particles protected by a thin carbon shell, about 1 nanometer thick carbon shell. But the protection is so good, you could leave that for half a year in semi-concentrated nitric acid, and the solution would remain colorless. So no cobalt leaching, because the cobalt was leached, if the shell was not perfect, was leached already during the silica leaching step. And you can see here, here is an empty shell, here is an empty shell. So about 20% of the shells are not perfect. From them, you leach out the cobalt, and the rest of the shells, the cobalt stays even under very corrosive conditions. Recently, Matthias Feyen again has extended this work to resin catalysts. We are working a lot now with polymeric resin catalysts, because biomass conversion reactions actually are done in aqueous solution at low temperatures. So resins are actually a very interesting class of catalysts for biomass conversion. And so we are interested in these materials. And Matthias he was the expert on making iron oxide nanoparticles. So he started with iron oxide nanoparticles, polymerized polystyrene or a polystyrene divinyl benzene around it, functionalized by sulfuric acid or SO3 treatment with acidic groups, and then we basically had magnetically separable acidic catalysts, which were here used for the reaction between benzaldehyde and ethylene glycol to result in this product. Magnetically separable, recyclable, well, it was not quite the same activity, but recyclable over several cycles by this just magnetic separation and then decantation. So there is many opportunities for producing magnetically separable catalyst and get a different, at least an alternative to conventional separation methods. Now coming to the last part, where I go on the engineering, again, quotation marks, on the engineering side to the smallest size scale, but with respect to the macroscopic engineering to the biggest challenge we are discussing actually nowadays, which is methane oxidation catalysts. Now, we are still wasting a lot of natural gas because we are flaring it in remote locations. It's not enough to liquefy, it's not enough to build a syngas plant to produce methanol or any other transportation fuel. So the best thing is actually to flare it because the greenhouse gas factor of methane is 25 times as high as that of CO2. So instead of just letting it out in the atmosphere, it's way better to burn it before you let it out. But of course, it would be even better to use it instead of flaring it. In principle, we can use natural gas, make syngas, make methanol or Fischer-Tropsch diesel or whatever we want. The problem is building a syngas plant is only economically viable if you have really huge plants. This is a process which has tremendous economies of scale. You need big plants. For many of the small reservoirs, it's not worth it. So that's why we are flaring it. And it would be quite interesting to have a direct methane oxidation pathway. I mean, chemists are looking for direct methane oxidation pathways for decades, maybe centuries even. And there are a number of approaches. The one we are following is actually based on the Periana system, which was really a milestone in methane activation approximately 15 years ago. Periana has described this type of catalyst. It's a platinum bipyrimidine dichloro complex. And that catalyst activates methane under actually harsh conditions, 220 centigrades, 24 bars, at 34 bars of methane in oleum, concentrated sulfuric acid 102%, so additional sulfur trioxide dissolved in the oleum. That's the engineering challenge I throw at you here, and it's actually getting worse when I proceed. It's not a direct oxidation of the methane, actually, in the Periana process. What we get is methyl bisulfate, so the methanol ester, half ester of sulfuric acid, but methyl bisulfate can be hydrolyzed to sulfuric acid and methanol. And so, in principle, if we look at the overall process, methane, sulfur trioxide in sulfuric acid gives you the methyl ester of sulfur, half ester of sulfuric acid, water, and SO2. This one is hydrolyzed to give sulfuric acid and methanol. Sulfur trioxide can be reoxidized to sulfur trioxide. That's conventionally what is done in a sulfuric acid plant. And so the overall process, if we add everything here up, is actually methane plus oxygen gives methanol. So it is a methanol oxidation process, even if it uses a transfer oxidant. I would call the SO3 a transfer oxidant. So this system has actually, by Catalytica, has been piloted to the liter scale in the 1990s, but then it was stopped because the system has three problems. First problem, the catalyst is a molecular catalyst which you have to recover from sulfuric acid or oleum. That's not a trivial task. Second problem, the catalyst activity was by about a factor 10 too low for commercial application. Third problem, and I say at the get-go, we haven't solved the third one yet. The separation of methyl bisulfate from the product mix is very difficult because the boiling points are very close and it's very difficult to separate. This one we haven't solved. The two other problems we have solved. First, going from a molecular catalyst to a solid catalyst. We were helped actually by a publication I saw in 2008 from Marcus Antonietti's group, and they had described the so-called cobalt triazine framework, which you get essentially by polymerization of a dicyanopiridine under quite harsh conditions. Then you get a highly porous network, which looks like this. Marcus has drawn it in a very regular way at that time, and I'm very grateful for it because otherwise I'd never recognized that this almost looks like the pyrimidal ligand of the Periana system. And this was one of the very simple ideas which basically should not work, but in this case it did. I at that time told the student working on this, why don't you just throw platinum on the solid and see whether the platinum doesn't coordinate like in the Periana catalyst to the solid. So we just added potassium tetrachloroplatinate, and indeed we got a catalyst which basically did the same as the molecular Periana catalyst. At that time, we couldn't do proper experiments. I'll tell you in a second why we couldn't do proper kinetic experiments, which we now have. But first, briefly, the analysis of the catalyst. So the platinum is really homogeneously distributed over this covalent triazine framework. It's basically platinum-2 in the system as analyzed by XPS. This is a 2 nanometer scale bar, so this is aberration-corrected high angle annular dark field STM. Each of these dots is actually a single platinum atom. So it's atomic dispersion of platinum in this covalent framework. Brad Schmelke was actually able to do platinum NMR on this solvent, which is quite a feat in itself. We did XAFs and modeled the XAFs. We did XPS also on the nitrogen. Basically, what it comes down to is all the characterization data we have for the solid indicate that the coordination motive is basically identical to the molecular Periana catalyst, and this explains why it has basically the same type of reactivity. Unfortunately, activity was still roughly a factor 10 for this solid, even a little bit more, too low for meeting the benchmarks which the Catalytica people had set. And then we started to explore all types of nitrogen-containing carbon frameworks as support for this type of catalyst. This is one of the more exotic ones, which, however, actually made not a bad catalyst, one has to say. Again, produced by Marcus Antonietti's group. He's not a co-author here, but Maddalena Tetrici worked with Marcus Antonietti at that time. They carbonized lobster shells. They probably were looking for a way to pay lobster dinners from grant money. They actually collected lobster shells, heated them, high temperature, protective atmosphere, and got a black material. We threw platinum on it, and indeed, the catalyst had an activity which was twice as high as the activity of the molecular platinum bipyramidal system Periana had described, and it's very reproducible. When we first had the result, we said, well, this may have been a very special lobster. Get a lobster from a totally different region in the world, do it again. They did it, and it's basically 10% deviation in activity. So that's a reproducible process, even with a biomaterial. Here now I can actually give you real kinetics. The way we did it before was just we filled a batch, pressurized with methane, after an hour looked at the products. We have now built a reactor where we actually pressurize with methane, can then follow the pressure drop, and from the initial slope, get kinetics, real rate data on this process with true turnover frequencies per platinum site. And as you see here, the lobster has twice the activity as the Periana system. And then we went further, looked at other polymers, at least 20 different nitrogen-containing polymers. We were successful with polyacrylonitrile-based ones. So we synthesized polyacrylonitrile, carbonized, and you get a nitrogen-containing, highly porous carbon, either microporous, depending on how you activate, or mesoporous, if you do it by a nanocasting. Don't want to discuss this. But then did again the catalytic evaluation. Here you see actually now a setup of the reactor, and this is why I say I buy new valves every like 3 weeks, because we have here oleum, and this is not 102%, this is typically 135% oleum, so really a lot of sulfur trioxide here. We pressurize methane at reaction temperature to the pressure we want. We open the valve. This is the 0 point of the reaction, so this is this increase in pressure here when we put methane onto the solution oleum and the catalyst, and then we record the pressure drop, and the initial slope gives us the rate of oxidation because the methane is oxidized and the methyl bisulfate is in solution. So 1215 turnover frequency for the bipyramidal system, the covalent triazine framework, approximately 1/5 of the activity. First, quite disappointing. If we carbonize the polyacrylonitrile at 650 centigrades, we have about 300, so also lower than the bipyramidal system. 850, even worse. But then if we really heat at high temperature, 1100 centigrades, this one gives you 4,000 turnover frequencies per hour, and the steam-activated one gives you almost 10,000 turnovers per hour. And this is now an activity which was set at the time by Catalytically as economically viable. We have calculated this. It's actually productivities of 0.5 kilograms methanol per liter and hour. And this is industrially acceptable. That you can make 50,000 tons per year in a reasonably sized reactor. Several, I think 20 cubic meters is what I calculated. And the very interesting thing for the Periana system is, while this here is the conversion versus selectivity curve for all other types of methane oxidation reactions, gas phase methane oxidations, high conversion, lousy selectivity, high selectivity, lousy conversion, this is totally different for the Periana system. Here we plotted many data points we had for our system, and what you see is your selectivity to methanol is, well, relatively high, almost 100%, and actually goes higher with higher conversion because we lose background reaction if we have sufficiently high activity. So this is indeed an interesting system. As I said, we still need to figure out the separation of the methyl bisulfate from the reaction mixture and the isolation of the methanol. This is still a tremendous challenge. But if that's solved, this could potentially be a method for making methanol without syngas from methane. With this, I would like to finish just recapturing. I have started by telling you how to place particles in specific pore systems. Iron oxide in the CMK, growing zeolites around nanoparticles. Also showed you the polyphenylene, the Suzuki coupling to produce a Suzuki coupling catalyst. Then I talked about these hollow shell catalysts, both for CO oxidation and for fuel cells. I had a short interlude on the magnetically separated catalyst, and finally came to the system which poses engineering challenges on the nanoscale. How do we create the right environment around the platinum? But now the challenges on the engineering, on the real engineering come. How do we handle the reaction in 135% oleum and then also get the separation sorted out? This one I just put in because I like it so much. For no other reason. We're exploring it catalytically. This is a nice particle. It's a Janus particle inside an iron oxide core. Here is a polystyrene half, and here is a silica half. So this is a particle with two polarities. You can now imagine, and that's what one of the students is working on, functionalizing catalytically this one in one way, this one in another way, and this would actually stabilize a Pickering emulsion between oil and water. So we could have a reaction with two catalytic functionalities on an interface. But as I said, I just put that in because I like this mushroom so much to see that one can go a step further. With this, I would like to finish. There were a number, many people. Basically, for all the projects, it's always the whole group contributing because people discuss, and this is how it should be. But specifically, I would like to thank the group leaders who worked on this. Anhui Lu, while he was still in my group, he's now in Dalian. Regina Palkowitz, she's now in Aachen. Claudia Weidenthaler is a group leader in the department. Students and postdocs who worked on different projects, our external cooperation partners for the fuel cell work, Karl Meyerhofer, Joachim Meyer, Volker Peinecke. A lot of the electron microscopy is done in collaboration with Osamu Terasaki, the methane oxidation with Marcus Antonietti, Maddalena Titrici, and we had funding support by a number of sources, but most actually from the Max Planck Society, which provides us with wonderful opportunities for scientific work. I would like to thank them all, but most of all, I would like to thank you both for staying with me, listening to me for so long, and for conferring this wonderful first medal on me. Thank you very much.
Thank you very much, Ferdi. It was beautiful, beautiful. We are a bit behind schedule. However, I cannot allow that we ask a couple of questions. So if there are some questions from the audience, it will be. Sotiris.
I echo Javier on his remark. And I was coming back to the very beginning of your presentation with the ammonia decomposition, which is the architecture that you have used. It's not the one that you think from the first point of view as a catalyst designer, because it's actually this design with the silica cells is when we put it to minimize the interaction of the core with the outside, minimize the ions. And I was wondering now if you are sacrificing two things. First, a lot of area of the iron oxide crystals. And second, if you are with this rather long pathways of to diffuse to the cell, actually you sacrifice speed in the reaction. And I was wondering if you could resolve it somehow with very maybe thinner silica cells, or let's say imagine right now, or having even less of these obstructions. How better the catalyst can be? Could it compete with whatever is out there?
This catalyst would probably not get much better. We have varied the shell thickness, and we don't get different in performance. I mean, we were, of course, worried about mass transfer limitations. So we checked for mass transfer limitations by varying the shell thickness, which you can do by just changing the coated amount of silica. And in the range we analyzed, we didn't see any influence. I mean, the shell is not very thick. It's a 10, 15, 20 nanometers. And the pores in the shell are on the order of 3, 4, 5 nanometers. So this is actually not much of a barrier for gas phase reaction. So we have no problem, at least for this reaction, ammonia decomposition studied under the condition with mass transfer limitations. It's not present there. Surface area, well, we haven't tried that. In principle, we could try to reduce the particle size of the iron oxide further, but one should say these syntheses are often rather tricky. And if you have much smaller iron oxide particles, it gets more difficult to get a homogeneous coating, which is identical for all the particles. I mean, I have to admit, I have often shown the examples which work best, like one often does. I would also never go and suggest that these are industrially viable catalyst synthesis protocols. They are, in most cases, way too complex, except maybe for the fuel cell system. There is actually industrial interest for the fuel cell system. We try to do that now in a continuous tube synthesis apparatus. But the design of catalyst this way gives you ideas how you would maybe go about doing it on an industrial scale, sacrificing some perfection, but making it much cheaper. And actually, BASF, I think I can say that, has triggered a big internal program after the first work published on these hollow shell with the gold inside. Because if you have this concept, put something in a hollow shell, you can think of many other pathways to making less perfect systems, but which keep the essential features of the system. So everything which I have shown you needs a lot of meticulous work, dedication, like I said in the beginning. Basically, maybe here one should... Rennie had this wonderful reference. Catalyst work should be approached humbly and with supplication, and the production of a catalyst, good catalyst, should be greeted with rejoicing and thanksgiving. This is perfectly true for these syntheses. They are tricky, but they give you ideas. I think that's the purpose.
Elma?
So, amazing work. What amazed me amongst the most was your Clayton results. So are you telling us then, if you extrapolate this further, that you could take table sugar with maybe a pinch of ammonia with some nitrogen inside, heat it all up, and then get this fabulous catalyst? Or is there maybe something hidden in the Clayton that
The chitin is a quite complex composite, and part of the reason why chitin works well is that this composite creates the high surface area and the porosity in the structure. This carbonization gives you really a highly porous structure, surface area. Again, it's microporous to a large extent. BET is also in the range of 1,000 square meters per gram. The chitin has the nitrogen functionality we need in the system. Frankly, we don't know. I thought when I saw the first data on the chitin-based system, there is some impurity in the lobster, and this is why I asked, get a lobster from, I think they took one from Brittany, the other from New Hampshire or something like that, from really different regions of the world, and it was totally reproducible, within 10%, which is the precision of the analytics. But I don't know why it works so well.
You couldn't take like regular table sugar or whatever other sugar.
We
Heat it, pulverize it, and then get the same.
If you take tables, well, first of you, like you said, you need the ammonia. You need some ammonia, which you could put in there, but table sugar doesn't give you porosity. So if you have table sugar, you basically need to do it with sacrificial templates. But frankly, I wouldn't exclude it. What I would do is I would use a highly concentrated sucrose solution or saccharose solution, whatever, infiltrate it into the pores of a silica, a highly porous silica gel, and then carbonize under nitrogen atmosphere. This is what I would probably do, and then try to leach the silica. You would get, if you coordinate then platinum, I think you would get some activity in the Periana reaction. I'm not sure what level of activity, we haven't done it. All the polymers, the nitrogen-containing polymers we used had some activity. Many of them, however, lost it. There the platinum was leached in successive runs, and we lost activity. But we are still working on the system, trying to optimize it further and understand it further. We also don't know exactly what kind of nitrogen functionality we need. I have shown you we have 650 centigrades, 850, nothing. At 1,100 centigrades, you get activity. If you look at the XPS, there is a lot of pyridinic nitrogen functionality, and that's a question how high you heat. That creates pyridinic nitrogen as compared to amine type nitrogen, which you form at lower temperatures. So we haven't fully understood it, but I wouldn't exclude it that it's possible with table sugar and ammonia under calcination, as a calcination atmosphere.
All right, a very final question, hopefully on magnetic nanoparticles.
I like your Kugelkohle. Magnetic Kugelkohle. How porous does it remain after you put in the metallic?
Oh, you reduce the porosity by maybe 20%. There is not so much iron in there.
Okay, but it's still a very porous material.
It's still a very porous material, and actually, well, if you steam activate afterwards, you lose some of the protection of your iron, but it's still a fairly porous material. Yeah. I don't have the quotes for the porosity values, but you lose from the initial Kugelkohle, which is actually a very good porous adsorbent, you lose maybe 20%. So that's still pretty okay.
Just a very quick question back to your first example with the silica and iron oxide. You would expect by those temperatures that you have iron oxide diffusion through the silica, even in an oxidative system, but your system
is highly reducive.
Highly reducing, so
yes.
like the iron nitride,
exactly.
That cannot diffuse through the silica.
Exactly. Otherwise, if we heat to very high temperatures oxidatively, you even get iron silicate formation. But this doesn't happen because the nitridation, the ammonia conditions form iron nitrides.
All right, so with this, I would like to close the discussion, and please join me for a round of applause to Professor Schmidt.
Thank you. Thank you. Thank you, Javier. It was a pleasure.